All right, grade 12, continuing our talk about electric fields. Here's a special case where we're looking at electric fields between charged plates. In the last episodes, we were talking about electric field emanating from charged objects, but here we have charged plates, which are very, very common in your electronic devices that are plugged into batteries. All right, so the objectives for today are learning how to draw electric fields between charged plates. Then we're going to learn how to understand how to calculate the field strength in between the charged plates. And we're going to calculate acceleration of charged particles that are entering those electric fields. That's a likely question you'll get on an exam. And this is just a really cool experiment. It's Millikan's experiment where he levitates particles using electric field. And that was used to discover the charge of an electron. So those are the four things that we're going to cover. All right, starting here. Here I have two charged metal plates. Imagine you had two flat metal aluminum or copper plates that are separated by a distance. And I was able to charge one of these plates positive and another plate negative. You can charge by friction or whatever you want, but most commonly we connect these plates to a battery. Okay, so I'm just gonna show what a battery looks like, the symbol in electricity. Okay, you often have batteries at home, like a 9-volt battery. This would be the positive terminal of the battery, and that would be negative. All right, so the flow of electrons would move. This plate on the bottom would become positive charge because it's connected to the positive terminal, and the negative side would become negative charged. Okay, now because these plates are not connected, no current is going to flow, and then charge would just accumulate on both of these plates, and they're separated by a distance. So as these charge plates are separated by a distance, if I would place a positive test charge, remember that's how we draw electric fields, if I'd place a positive test charge anywhere in here, I would notice that the positive test charge flies upwards. And that's how we mapped out the positive test charge. Now notice that the spacing of those arrows are equal. So what does that mean? Well, if they're equally spaced, that means that the electric field in between these two plates is constant. It's uniform. All right. So right in the middle here, I have the same electric field here as I have over here, which is a little bit different than when we had just a general positive charge, okay, that has an electric field in outer space. We would notice that the electric field is not uniform because these arrows get spaced out over here compared to over here. So the electric field would have been stronger here than over there. But one thing that you need to know, inside of charged plates, the electric field is uniform. Okay, so that's how we draw them. In between the plates, you would have straight arrows that are equally spaced, and on the end I would have a positive charge that would fly that way, but then would be attracted to that negative charge. So we have these end caps that go that way. So when drawing electric fields, make sure you have the end caps and you have these arrows that are equally spaced. Okay, that's usually one mark, and we need to know the distance. So just here's a diagram explaining the deficiency of electrons on one side, excess electrons on the other, and the electric field on the inside attached to the battery like I showed up there. Okay, positive side, positive charge, negative side, negative charge. So the second question that we're going to look at is, how do I calculate the strength of the electric field between these plates? Okay, so in this case, let's imagine that two charged plates with a potential difference of 1,000 volts, so that's the potential of the battery, which we're going to learn in the next class. We're going to talk about what is voltage, but for now we're just going to use it. 1,000 volts of energy are separated by 1 centimeter. So if I would draw these plates out, I have a positive plate up here, negative plate up here, and they're connected to a battery that is 1,000 volts, and the distance separating this is 1 centimeter. So if I was to draw the electric field, okay, in this case it's going down, equally spaced arrows, look something like that. And if I was going to calculate the electric field strength symbolized by that, there's a formula for it in your data booklet that looks like this: voltage divided by distance of separation. So that if I know the distance of separation between these two plates and I know the voltage applied, I can calculate the electric field strength. Now, I'm not going to go into detail. I'm sure in Cognity they went into detail deriving that equation, but in our next video I will derive this from our understanding of what is voltage. It becomes a little bit easier that way. So if I take the voltage, 1,000 volts, and I divide it by 0.01 meters, which is 1 centimeter, that will give me, okay, now I just got to put 2 more zeros in there. Wow, 100,000 newtons per coulomb, or according to IB talk, 100,000 newtons per coulomb. Okay, remember, this is the symbol that we need to use where we never use fractions in IB, we use the exponents. Okay, so 100,000 newtons, there's 100,000 newtons of force for every coulomb of charge that I put in there. So if I had, let's say, a proton, okay, that's my proton, and I wanted to calculate the force acting on that proton, I would take the electric field strength times the charge of that proton would give me the force. So in that case, 100,000 newtons per coulomb times the charge of a proton, which is 1.6 times 10 to the minus 19 coulombs, would give me the answer, which would be 1.6 times 10 to the minus 14 newtons. Okay, that's how much force would be acting onto that proton. So just giving you a sample calculation. Once I've calculated my electric field strength, I can then calculate force by taking the electric field strength and multiplying it by the charge of a particle. So how can I use these two things to talk about the motion of a charged particle that's traveling between plates? In this example that I've drawn over here, we have an electron. Oops, let's change the color of that so we can see it. So this is an electron. And that electron is flying with a velocity. Let's say that velocity is like 1,000 meters per second, okay? And let's say that the electric field strength between here is the same as above, 100,000 newtons, okay, newtons per coulomb, okay, like we did from up here. So imagine this is a multi-part problem. I had that set up, and now I applied it here. So my electric field strength is 100,000 newtons per coulomb. How would we be able to predict the path that electron is going to take? So often you'll get a question showing, draw the path that electron will take when it flies into these plates. Okay, so when the electron starts to fly between these plates, it's going to experience an attractive force in the upward direction. Okay, this is the electric field showing in that direction, but negative charge is going to be going in the opposite direction. So it's going to experience a force acting upwards on it, or perpendicular on its path. So what's going to end up happening is that electron is going to experience a parabolic path, okay? Just like when you throw a ball, if I threw a ball, it's going to fall towards the ground because gravity is acting perpendicular to its path. In this case, that force is acting perpendicular, so it's going to have a parabolic path. And when it leaves, if it doesn't hit the plate and it leaves, it's going to leave with a straight line because there's no more force acting on it. So it'll just continue straight on that trajectory because there'll be no more electric force acting on it, okay? So I could easily ask you questions regarding kinematics, okay? If I knew that this distance here is, let's say, 0.8 centimeters, okay, and I have the speed of that, and I have the force, you'd be able to calculate, for example, how much time it would take for that electron to fly through and hit that base. All right, so then you'd be able to predict, will the electron with that velocity be able to make it out, or will it crash into that base? I have some practice problems. I don't want to go through the answer here because I want you to think about how would you, A, calculate force, okay, and then use the force to calculate acceleration. Okay, so remember that you have to go F equals ma. So once you've calculated the force, then you'd have to apply F equals ma, where m is the mass of an electron, F is the force you calculated. You should be able to calculate acceleration. And then the last thing after doing that is apply acceleration in kinematics, like we did in chapter 1 last year. Okay, so then you would have to think about how you would do that. I don't want to give you that answer. I really want you to go back and think, stop this video for a second and think, for example, if I gave you a force here, or you can even calculate the force, the charge of an electron and that electric field strength, you could calculate that force. And then from that force, you can calculate the acceleration. And would you be able to design a question where you're applying acceleration in kinematics? That's a good thing for you to do at this point in time. All right, and then the last thing I wanted to present was just now that we have a knowledge of what electric fields look like in between plates, I can show you the first experiment that Millikan designed to discover the charge of an electron. And he did so by taking oil drops that have a known mass. He dropped oil drops with a known mass in between two charged plates. And as they were dropping, he zapped them so that they would have one electron on each oil droplet, or roughly around 1 electron, 2 electrons. He'd give them little static shocks. And he would adjust the voltage so that the oil droplet wouldn't fall to the ground. So the oil droplet experiences a gravitational force, and it normally would fall to that plate. But if he adjusts the voltage, he creates an electric field in here that would repel that oil droplet and then apply an electrical force upwards. So if that electrical force upwards matches the gravitational force, that oil droplet can become suspended and levitate. And by doing that, he was able to come up with an intricate method to measure the charge of an electron. So here is the actual setup. Here's a window. He can be looking inside. He's dropping oil droplets in, and he's just adjusting the voltage somewhere over here. Here's a knob for the voltage. Adjusting the voltage until all the oil droplets stay suspended. And at that point, he can read the voltage. He knows the distance here, so he can calculate the electric field, and then he'd be able to then apply some equations. So in that case, okay, when the oil droplet is suspended, let's change the color here, the force of gravity is equal to the electrostatic force. Okay, so then the mass of the oil droplet times the acceleration of gravity is going to be equal to my electric field strength times the charge of an electron. Okay, if that had 1 electron, if this object has 1 electron attached to it. Okay, the electric field strength times the charge of the electron. Okay, and how do we calculate the electric field strength? Well, I'm just going to rewrite this. M times G is equal to the voltage divided by the distance separating the plates. That's my electric field strength, times the charge of an electron. So in his experiment, he's just trying to solve for the charge of the electron so he can do some algebra, okay, to cancel that out. And what he would get is the distance of the plate between the plates times the mass of the oil droplet times the acceleration of gravity divided by the voltage is going to give you the charge of an electron. And when he did that, he found that the smallest charge of an electron that he could measure using this experiment was equal to 1.6 times 10 to the minus 19 coulombs, or negative 1.6. And that is how we discovered the elementary charge from this relationship. Distance between the plates, the mass of the oil droplets that he was dropping, G, the acceleration of gravity, and V, the voltage when that oil droplet became suspended. So when this oil droplet became suspended, he reads the voltage, he knows the distance between the plates, okay? So knowing the voltage and the distance gives me my electric field. He knows the average mass of an oil droplet, okay? That's everything he needed to be able to calculate the charge of an electron. One of the most brilliant experiments I've seen. There's many brilliant experiments that came on that time, and that one's so simple and elegant and very brilliant. Okay, so hopefully you learned a little bit about electric fields between charged plates in this video.